Excuse me, just step on it. So first of all, while we're getting set up, I do want to thank Michael and the organizers. It's really an honor to be here. As Michael said, I spent 5 years in Scotland, and I tried to get here as often as I could, up to 3-4 times a year, because it is one of the outstanding places in the world to do the type of work that we do. Perfect, gotcha. And so what I'm going to hope to do today is I'm going to talk about the loading parameters and how we want to load our musculoskeletal system to optimize performance, but also minimize injury. And really that's what we try and do, is we try and get to the balance. Because we know that as we increase performance capability in an athlete or in an individual, that individual is also going to increase their risk of injury. And so what I hope to do today is I hope to show that we can understand these things at a number of different levels. And what I'm going to try and do today is I'm going to try and break things down to the molecular level and then build them back up through the athlete. Before I start, I do have to acknowledge and disclose things. A lot of the work that I'm going to talk about today is done by some postdoctoral fellows and some researchers in my laboratory. So people who've done the work are listed here as my lab members, a number of different collaborators that I've had. I'm going to talk about some of the work with Helgi Amtor today. But I also do have to acknowledge that I am paid by PepsiCo, Opta, MSM, Advanced Muscles. So there is some, you do have to take some of the things that I'll say. None of the research that I'll present today at this talk is going to be sponsored by anybody outside of the NIH and the U.S. Department of Veterans Affairs. Okay, so what I hope to do today is I hope to be able to, by the end of today, you should be able to tell other people about the role of matrix and strength. So how does the extracellular matrix play an important role in our strength? And as Michael said, I started as a strength coach, and I began working in this area when I started working with British Cycling. Because British Cycling, what they were doing at the time is they were saying, well, yeah, you're an expert in muscle growth, but we don't want muscle growth. We want to get stronger without making the muscle bigger. And textbook tells us that muscle is only as strong as it is big. But what we've learned since then is that a lot of the strength is actually coming from non-muscular components. So today, you should also be able to prescribe loading parameters to enhance musculoskeletal health and performance, explain how the matrix can be modified by load, and then, for those of you who are not molecular biologists, you should still, at the end, hopefully I'll be able to describe this in a way that's accessible enough for everybody so that you'll be able to kind of talk about a molecular pathway that leads from the types of loading that we do, the types of exercise or training that we do, to increase matrix production and make our muscles, tendons, ligaments, and bones work better. All right, so what we're talking about here is we're talking about everything from the muscle extracellular matrix, so that's shown beautifully here, that is this matrix that's outside of the muscle cells themselves. All right, so in a muscle, 95% of the protein that we see in a muscle is going to be cellular protein. A lot of that is nuclear protein, so there's easy to get good ideas as to what's happening inside these muscle fibers. But outside these, in this extracellular matrix component, we still don't understand very well what's going on and how this functions in order to improve our muscle health and functionality and performance. If we contrast that to very tight connective tissues like ligaments, whereas the muscle extracellular matrix is kind of attaching and connecting all of these muscle fibers together, and I'll show you that a little bit in a film a little bit later, what happens with a ligament is now you've got a material here that is almost 95% extracellular matrix, whereas before I told you 95% of a muscle is actually cellular material. So what that means is there's a lot of extracellular matrix which is made up primarily of collagens, and these collagens are mostly directional, and the important thing about a ligament is it's going to attach a bone to a bone. So that means that it's attaching two very stiff structures together. Because it's attaching two very stiff structures together, the stiffer this is, the better it is. So for a ligament, we know that the stiffer the structure is, the better it is. For all connective tissues, this is true. So these are a bunch of different tendons. What you can see on the bottom, on the x-axis, is that the stiffness, or the modulus there, that modulus is such that as the modulus or stiffness goes up, the tensile stress goes up. And what that means is that the stiffer the structure is, the more force it takes to break it. So for a ligament, that's wonderful because you're attaching two very stiff structures. So if I make that knee joint less lax, that stability is going to increase or decrease the rate of ACL rupture. Because the stiffer the ligaments are, the less movement the joint has, the stronger it will be, the more resilient it'll be. And so there's two real things that go into making a ligament or a tendon or any connective tissue stronger. The first one is the amount of collagen. And I've just depicted the collagen as these little triple helix structures here in the image. And so what we need to be able to do is to have a strong tendon or ligament or connective tissue is we need to have lots of these collagens. If we make more of them and we get this structure bigger, that is inherently going to have the potential to be a stronger tissue. But that's only one component. The second component is what we call the crosslinks. And I've just depicted them here as these little bands of red that when you get it at rest, they're relaxed. As you pull on the tension, as you provide tension on this tissue, those actual crosslinks stretch, connecting up the collagen molecules. So we know that if you don't have these crosslinks, the stiffness of your tissues go down, and that as you increase crosslinks, the stiffness of your tissue goes up. Okay, so the stiffness of your extracellular matrix, whether it's collagen, whether it's the ECM itself, tendons or ligaments, comes down to how much collagen you have and how cross-linked that collagen is. As we get older, we get sugar cross-links. So as our blood glucose goes up, we get more sugar. Those sugars can increase the cross-linking. But when we're going to talk about this as normal physiology, we have an enzyme that actually does all the cross-linking. And that enzyme is called lysyl oxidase, and it's really important for being able to cross-link these structures together. And as you increase how much lysyl oxidase there is, the stiffness goes up, and the result is the tissue is going to be stronger. And if that's a ligament, that's great. I'm making a distinction here because a tendon is different than a ligament. And if you ever go back to your physiology that you've taken in your university or your medical training, basically what you'll see for a tendon is this one sentence. And that's all there is in the whole textbook of all of your physiology. And that sentence says, tendons bind muscle to bone. They don't even have the two little things that I said. I put in compliant to stiff. And that's the really important thing. Because a ligament binds a stiff structure to a stiff structure. And that means when I pull on it, the stiffer the better. Tendon has a very compliant, a very flexible tissue in the muscle. It's a very loose tissue. And then on the other end, it's got a very stiff tissue, the bone. So what it does is it does this unique mechanical function in the body. And what it does is it transitions between a very compliant tissue to very stiff tissue. And that's extraordinarily difficult to do. If you go to an engineer and you say, look, we've got two structures that we want to connect together, and one of them is very, very stretchy, and the other one is very, very stiff, they'll get very concerned because they know that that's the structure, that interface between the stretchy tissue and the stiff tissue is the structure that's going to break down. And that if you don't have proper adaptation, that structure is going to be really dangerous as a point of failure. The most important thing for us to know here is that unlike a ligament, the stiffer the better because it's got stiff structures on both ends. Here, because you have a compliant tissue on one end and a stiff tissue on the other, if you just increase the tendon stiffness, that's going to put that muscle at risk of injury. And what you see when you're training athletes is you see these people who are increasing their speed, who are getting to the point where they're the fastest they've ever been. And what do we see happening a couple weeks later? They're rupturing a hamstring. They're pulling a muscle. You see it in the world and Olympic championships, especially in the 200 and 400 meters for the men's races. What they've done is these athletes have increased the stiffness of the tendons so that they can increase their performance, but then the muscle is a little bit less strong than the tendon is stiff. And so now when they hit the ground and they're trying to run fast, what happens is instead of the tendon stretching a little bit, now the muscle has to stretch when it's lengthened, and that's when you rupture a muscle. So how does a tendon do this? How does it take a compliant tissue and transition it into a stiff one? Well, if we when we originally did these experiments, we had to do these in animals because what we wanted to do is take out a muscle, take out the tendon, take out a bone, hold on to the bone and hold on to the muscle, and we drew little lines on the tendon. And the lines that we drew close to the muscle, they stretch more easily than the lines we draw close to the bone. And that looks like this when we do all the calculations. The red line here, that's the end of the tendon near the muscle. And what the data is showing is strain and stress. All that means is how far it pulls on the x-axis and how much effort we have to put into it to pull it that far. So if it comes way to the right, that means that it doesn't take much effort to stretch the tendon. If it goes straight up, that means that every time you pull it, it takes a lot of effort and it's very stiff. So this red line is very compliant, the green line is very stiff. This data comes from one tendon. And what you can see is that the part near the muscle is this red part, and it's very compliant. The part near the bone, that's the green point. It's as stiff as the bone, even though we're looking at the tendon. And so what a tendon does is it's got regional mechanical properties. Near the muscle, it's stretchy. Near the bone, it's stiff. And it transitions, and it does that transition, and that transition is the health component of the tendon. This muscle end of the tendon is what we change when we train. If we train in certain ways, we can make that stiffer, and the performance of our athlete is going to go up. If we train differently, we can make it less stiff, and the performance of our athlete is maybe going to go down a little bit, but their health is going to improve. Okay? So the next thing is that these mechanics aren't always the same. Tendon is what we call viscoelastic. And what that means is that it behaves mechanically like an elastic material and like a liquid. So if you consider viscoelasticity, what we're thinking of something like a swimming pool. And if you put your hands in the bottom of the shallow end of a swimming pool and you let yourself down slowly into the water, you'll barely feel when you leave the air and you get into the water. Because when you move slowly, the water molecules can work as individual molecules, and they'll go around you with very little resistance. As you increase the speed at which you enter the water, you increase the amount of resistance because there's not enough time for the water molecules to move around you slowly, so they begin working as a sheet. So as we go from working slowly to loading a tendon slowly to loading the same tendon moderately or very fast, what happens is it increases the amount of stiffness of that tissue, just like the water increases stiffness. So if instead of letting myself down slowly, I run from the side of the pool and I jump in and I land on my belly, now my belly is red because I've done a belly flop, I've moved faster. So the water doesn't work like individual molecules, it works like a sheet, and that sheet is almost like a solid, and the result is that I've hit a solid and it has provided me with a lot more resistance. I'm going to get, that stiffness is going to mean that I have to get all that energy on my belly and I'm going to get a red belly. If I go up to the 3-meter board and I run and jump off, now it's not just a red belly, now I'm going to the hospital. Because what I've done is I've gone to such a distance that I'm going super fast when I hit the water. And when I hit the water, that water is now super stiff relative to where I am. And by the time I slow down enough so that the water molecules move around me, it's too late. I've already absorbed a ton of energy. Okay, so how does this relate to what we're going to talk about, which is loading? Well, when we look at how a muscle and a tendon come together, they don't come together like two tissues or two things that just come together and just meet in the middle. Okay? What they do, the muscle is on the left side here, the tendon is on the right. This is the myotendinous junction. And what you can see is just like you would have done if you were a kid like me and you get into trouble, you and your friends would go jump fences. You don't go jump fence and help your friend over the fence by putting your hands together like this. You don't go down and have them step into your hands when they're just together because all that's going to happen is you're going to step right through. So what do? You link your fingers together. Now when you put your fingers down, now you can lift up your friend because what you've done is the same thing the myotendinous junction does. You increase the surface area of attachment. you can see that you can now attach at a lot of more surface. But the second and almost more important thing is now when I load, when I pull my hands apart, now what I'm doing is I'm loading with what's called shear. That's two things sliding past each other. And when that happens, what you do is the collagen molecules that are close to this muscle are going to get pulled in different ways. So what you can see is this one comes in, and what's going to happen is you're going to get different pull rates. You're going to get shearing. And when that happens, the little crosslinks that go between the collagen molecules get broken. And as I said before, the collagen molecules, the crosslinks make them stiffer. So if we break those crosslinks here, because we have this shear force, what's going to happen is that this region of the tendon is going to be less stiff. And as we get further and further, closer and closer to the bone, you have less and less shear, and so it should get stiffer along the length. So if this is true, then if we inactivate the muscle, we should see a change in the mechanics of the tendon. And that's what we did. In this situation, what we did is we just cut the nerve to the muscle, and we did the exact same muscle that I showed you before. And that red line that used to be down here and to the right, now it all shifted up. Because when you don't have the muscle contraction, you don't get the shear. If you don't have the shear, you don't break crosslinks close to the muscle end of the tendon. And as a result, you don't keep the stiffness of that tendon, or you don't keep the muscle end of that tendon less stiff. Okay? So we've all done this. We've all seen this in our athletes. If you're a physical therapist, you have somebody who has a broken bone in their foot. You put them into a boot for a couple of weeks. So after 4 weeks, you take them out of the boot. They get out and they run again. Oh, they look a little faster. Oh, that's great. Then what's the second thing that happens? They look faster because they're stiffer, because they can get more energy back from the run. And then the second thing that happens is they pull their calf muscle because they're stiffer, they perform better, but they don't have the health. And so what we have to do is we have to do slow, heavy loading, because slow, heavy loading increases the shear at the myotendinous junction, and it's going to bring that muscle end of the tendon back. So the viscoelasticity comes into it because when we load slowly, those collagen fibers act as individual molecules, and they slide past each other. When they do that, you break crosslinks, and the result is that you end up with a less stiffness in the muscle end of the tendon. When you load quickly, now the tendon collagen works as a sheet, and instead of breaking crosslinks, you don't break the crosslinks because it's working as a sheet. And every time you exercise, no matter whether you exercise quickly or slowly, we're going to increase the activity of that enzyme lysyl oxidase. And so what happens is we're always adding more crosslinks. The question is, did our exercise, did our loading break crosslinks down, or did it not break crosslinks? So if I load you quickly, you're not going to break crosslinks, you're going to add new ones, you're going to get stiffer. If I load you slowly, you're going to get the sliding past of the collagen molecules, you'll break a lot of crosslinks, you'll add some back, but it's not as many, so you'll get less stiff. So in one case, we're loading quickly to increase performance, and the other case, we're loading slowly to increase our health. All right, so what I've told you so far is that tendons connect muscle to bone, whereas ligaments attach bone to bone. That means that the ligaments are doing stiff to stiff, and the result is that the stiffer they are, the better. Whereas a tendon, because it has a compliant end and a stiff end, it can't just be stiff on throughout. It has this regional mechanics that are going to be really important to its functionality. The primary protein within these sinews, within tendons and ligaments, is collagen, and the collagen provides the backbone, and then these crosslinks provide an extra layer of stiffness. And there's two types of crosslinking. There's the lysyl oxidase crosslinks that are normally made in everybody, and then there are these sugar crosslinks which are increased in diabetics and increased as we age. And these crosslinks are less easy for us to metabolize, and it's one of the reasons why diabetics suffer more tendon and ligament ruptures and injuries, and suffer a lot of other musculoskeletal as well as other health-based issues. The water within our tendons and ligaments means that they're viscoelastic. If we load them slowly, what happens is they're going to be less stiff. Because they're less stiff, you can get more movement of collagen molecules. And because you get more movement of collagen molecules, you can decrease the crosslinks and keep that tendon a little less stiff. All right? Okay. So now what I'm going to do is I'm going to shift gears and say that what we want to do is we want to understand how to make these structures bigger and stronger. We want to improve tendon and ligament function. But in order to do that, what we felt we had to do was come up with a model. And the reason that we had to come up with a model was actually work from Katja Hennemeyer, who's out here. And basically what she had shown after consulting with an expert scientist and her father and using the bomb pulse to actually figure out how quickly collagen turned over within the tendons, what she did was she collected in 2000 the central core of the Achilles tendon from a bunch of individuals. And I didn't put all the individuals on the graph, but that's a lot of them. Because what she found with this study was that as you look at how much C14 content, because C14 didn't really exist in the environment to any great degree before the 1930s, you create atomic bombs, you then test atomic bombs in 1962-ish. Now they've got a treaty, so you can't explode them over ground. So now what happens is you get exponential decay of the collagen. So if you have a fast turnover of your tissue, basically what you'd expect is the collagen should, or the C14 content should be equivalent to when you collected the tissue. If it turns over slowly, it should follow the bomb pulse. And what she found is that the collagen within the central core of the Achilles didn't turn over after you were about 17, 18 years of age. So the central core isn't changing a lot. The other reason that we thought we needed a model is because that's what a tendon looks like over there. Again, 95% of the protein is extracellular matrix. So I do a lot of muscle work. And when you get a muscle sample, what you do is you take the muscle sample and you powder it under liquid nitrogen. And it makes this beautiful powder. And you look in and there's this big white thing, and you pick up the big white thing and you throw it away. That's the tendon that I just threw away. Because basically it's really, really hard to do biochemistry on this tissue. It's an extraordinarily difficult tissue to work on because there's very few cells and there's lots of matrix. And that makes it really difficult to do biochemistry. So what we did is we came up with a way that we could model this in vitro. And so, as Michael said, I work in Davis, California, which is an hour and a half from Lake Tahoe, California, which is one of the world's great ski areas. So right around now, there's beautiful snow, which means that there's lots of people going up for the first or second time of the year. And then they're going to come down the hill. They're going to get their ACL repaired at our local hospital. And we're going to take the remnants of that ACL, and we're going to isolate the cells from that. So we have human ACL cells. And then what we do is we put those human ACL cells into the gel. And we make the gel from fibrin, which is a material that all of you are very familiar with because all of you have gotten a scab of some sort, and that scab is made up of a fibrin gel. So it's a material that your cells know of really well. And then what we do is we make these little anchors. And the anchors that we make are made from calcium phosphate cement, which is very similar to what your bones are made up of. And that's the mineral component of your bone is the calcium phosphate. So what we have is we have two bones, and we have ligament cells. Within 7 days, they're going to form these really nice looking ligaments. And then what we can do is we can mechanically test them. And because what these tissues do is they function to resist load. So if we mechanically test them, now what we can do is we can manipulate the environment, and we can see what changes in the environment due to the strength of the tissue. And then we can take it and we can do biochemistry, and we can do all of this because there's many more cells in here than you would see in an adult tendon. And this is a tendon after 2 weeks, and what you can see is they actually get pretty strong. This is a metal pole here that has a force transducer on it, and you can see that the ligament is actually bending the metal pole. And the other thing to notice is that it's an avulsion fracture, which means that actually the interface between the muscle or the tendon and the bone is the weak spot. So it's very similar to what you see in vivo. The other thing that you can do is now you've got a toy. So what we can do is we can 3D print these little grips, and now what we can do is we can make machines. We make machines like this one that can exercise it, because nobody knows what exercise, or nobody knew what exercise was best for your tendons and ligaments. And so what we can do is we can do, within a couple of weeks, we can do every different possible combination of exercise. And what we found is that it didn't matter how far we stretched them It didn't matter how often we stretched them. What seemed to matter most was how long we stretched them, so the duration. So what happens is about 5 to 10 minutes after you start stretching, the activity of a lot of proteins that are important in tendon and connective tissue function, specifically this protein we're going to talk about a little bit today, ERK1/2, they get activated within 5 to 10 minutes. This is an early study that showed 15 minutes, and then already by 60 minutes, it comes down. If we look at 90 minutes, it's back down to 0. And so what we learned is that it didn't matter if we did lots of movement, like if we were to run versus walk, or if we were to do full range of motion versus limited range of motion work. Any type of tension on the tissue itself would activate these pathways. And then they would turn off no matter how long we went, they would just stay off. And so what that said to us is that these cells are becoming refractory. They don't sense the signal anymore. And this is very similar to your bones. That's tibial bone mass on the y-axis here. This is the loads per cycle on the left. You can see that already by 40 loadings, if you jump 40 times today, that's enough to get maximal tibial bone growth. So that's maximal bone effect. Only takes 40 loads. If you do multiple loads a day, it takes about 6 to 8 hours before your bones can sense that you've done another stimulus. So what this would say is that very short periods of activity followed by long periods of rest are best for connective tissue. There's a nice Japanese study that shows that if you take young girls and you have them jump as high as they can 6 times a day, that's enough to increase their bone mass significantly. So what this is telling us is that what we're seeing is that the cells are becoming refractory. And sure enough, when we stretch for 10 minutes, you can see a nice activation up here. If we then wait a half an hour and we do another 10-minute stretch, you can see that it doesn't turn on the same way. 1, 2, 3 doesn't improve, but it takes a full 6 hours before you see the cells are able to respond again. And so what this tells us is that if you go 5 to 10 minutes, have 6 hours of rest, 5 to 10 minutes, 6 hours of rest, it should have improved functionality for your tendons and ligaments. And in fact, when we did this in our engineered tissues, this is stretching continuously. So that's 24 hours a day going, because we can do that because it's a little tissue that sits in a dish. Or we only did 4 sessions of 10 minutes with 6 hours of rest in between. What you can see is the intermittent, even though this is only 40 minutes and this is 24 hours, you get actually double the collagen increase in these tissues than if you did continuous work. So what this is telling us is short periods of activity with long periods of rest are best. Our work shows that tendons and ligaments work that way. The work by Baar and a lot of other people show that that's how your bones work best as well. That your bones, and actually there's good evidence now that the cartilage works similarly, that short periods of activity with these long periods of rest are going to be optimal. All right, so maximal effect is seen after 5 to 10 minutes, takes 6 hours, and if you do these heavy loads, for about 5 to 10 minutes, you're going to optimize the performance of your connective tissue. Okay? So most of what I've talked about so far is in the actual tendons and ligaments in the matrix there. What's really underappreciated is the extracellular matrix within the muscle. And this is where we've been focusing a lot because of that story I told you about British cycling. They want to get stronger without getting bigger. And so the question is, how is that working? And they've done it. They show me data that shows, look, here's their body weight, here's their muscle weight, here's their strength. It's going up significantly. It could be neural adaptations, but these are elite athletes who've been training for a long period of time. It's probably not neural. And so what we were thinking is that if they were better able to transmit force, they would be better able to take the force that the muscle makes, and get it to the bone to produce movement. Think of it this way. If I take a big rock in the middle of the stage here, and if I were to put a rubber band on it and pull on it really hard, all that's going to happen is the rubber band's going to stretch. The weight's not going to move. If instead I put a rope on it and I pull on it, the rope is going to stretch a little bit, but then at a certain point, now I'm going to be able to pull the rock. But if I put a metal rod there, and if I pull the metal rod, because the metal rod is stiffer, as soon as I apply force to it, the rock moves. Okay? The stiffer that I can get the connector, the faster and the more force is going to go to the object I'm trying to move. So if we make these structures stiffer, we should be able to increase force. So when we talk about matrix within muscle, There's the fibrillar collagens, type 1, 3, and 5, that are really the big girders within this structure. These are the things that are the load-bearing structures. There's type 6 collagen, type 4. Type 4 just surrounds all of the fibers. That's your basal lamina. And then you get into a bunch of proteins within the muscle that people have heard of, like dystrophin and the dystrophin-associated proteins. Dystrophin's famous because if you don't have it, you get a disease. But what most people don't realize is that actually a lot of these proteins, collagen 6, collagen 5, if you have mutations in those proteins, you get a muscle disease as well. And what I've told you is this matrix is important in connecting muscle fibers together. And that's best illustrated in this beautiful movie set from Dennis Claflin, who is a colleague of mine when I was working with John Faulkner at Michigan. You can see a normal muscle. This is the pedicle muscle, so the muscle off the bottom of the foot of a mouse. And the reason that he used that is because it's one fiber thick. So you can actually image the whole thing. That's a normal muscle. It's just doing isometric contractions. Looks completely normal. If instead you take a dystrophic muscle and you do the same thing, because it's not connected, the fibers aren't connected together because they don't have this matrix, what you're going to start seeing is the fibers are individually going to slide past each other. And when they do that, this is going to be 10 contractions. At the end of these 10 contractions, this muscle is going to be completely destroyed. And so what's going to happen when this dystrophic muscle exercises is that it has to regenerate itself. Because instead of contracting all together as one unit, what happens when you have a dissociation between the inside and the outside is the muscle fibers now slide. And when the muscle fibers slide, they open up holes in the membrane. That allows calcium in, which causes contractures like these. All right? So if you take a look at all of the diseases, Ehlers-Danlos is the collagen 5, you've got muscular dystrophies associated with collagen 6. All of these structures are important for muscle function. So if you don't have them, the muscle's not going to function well because they're not going to be linking all of the fibers together. And they're not going to be transmitting force appropriately. Because even though we think of a muscle as shortening from tendon to tendon, 80% or more of the force actually goes laterally first and then along the muscle to the tendon. And so in order to transmit the force laterally, all of these collagens, all of this matrix has to work properly. So the question that we had is, well, how does this work when we're doing loading? And so we use these animal models because they allow us to see big changes in a short period of time. So what we can do here is we can cut out the calf muscle of a rat, leave behind the plantaris muscle, which in a rat is actually a sizable muscle, and then over 2 weeks that muscle is going to grow about 70%. So a really big growth. It's not physiological. I'm not trying to say it's physiological. But what we can then do is we can look at see what happens within the muscle fibers. And if you look, there's two things that happen. First, as you'd expect, the fibers get bigger. Because there's more load on it, the fibers are going to get bigger. But what I also want you to see is that there's more of this white stuff on the outside as well. And that's the collagen. And if we actually look to see how much collagen there is in the muscle, this is the percent collagen in the control muscle on the right on the left versus the overloaded muscle on the right. What I want you to see is, the amount of collagen goes up, but the percent collagen goes up as well. And what that means is as the muscle is growing, you actually have more collagen synthesis than you have muscle protein synthesis. So you're getting more collagen than you are in muscle protein. And in fact, if you look at collagen 5, gene expression's up 120-fold. The collagens 1 and 2, it's up 20 to 30-fold. So what my colleague Helgi Amtor did is he used a drug called halofunganone to block collagen synthesis. And you can see that it worked because he did overload here. Collagen protein doesn't go up in the halofunganone group, but it does go up in the control. Had no effect on the ability to grow the muscle fibers. The muscle fibers, if anything, looked a little bigger. The important thing is here on the right, strength. The maximal isometric strength, when you treat with the anti-fibrotic agent, is actually 50% less than when you had the control group. So if you don't make new collagen, you actually don't get as much of a strength adaptation. You actually only get 50% of the force that you should get. All right, so this extracellular matrix is really important. And so the question is, how does this get regulated? Well, turn to experts in the area. So Delphine Dupriez in Paris, she'd shown that this gene EGR1 is really important in load responsiveness. And others have shown that in tendon, like Delphine had shown, there's really, EGR1 plays an important role. It's one of the earliest genes activated in a tendon by exercise. And so what we did is we actually looked in the muscle. And I actually first went back to a work that we had done during my PhD where we had done gene array analysis on muscle after exercise. And the number one gene that we had found as being upregulated by the exercise was EGR1. By an hour and a half, it's up 120-fold. That's the biggest increase in any gene that we find in muscle after you do exercise. The protein, we now have shown that it goes up about 6-fold between an hour and a half and 3 hours after the exercise. And then what you see is that there's this increase in all of the fibrillar collagens, which begins around 12 hours, and you see it 36 hours, it's significant, 48 hours, it's still going up. So what we do is we do a single bout of exercise, we get an increase in EGR1 mRNA, an increase in EGR1 protein, and that increase in EGR1 protein, Delphine has shown EGR1 can bind to the promoter of a number of different collagen genes and drive collagen synthesis. So how is it controlled? Well, if you remember that protein that we had looked at for the tendons, the phosphorylation of ERK, when we look in muscle cells, if we activate ERK using a drug, we see a nice increase in ERK activity that goes down, just like we see when we stretch our muscle or our tendons. EGR1 mRNA goes up, peaks about 30 minutes in and comes down, and EGR1 protein goes up and peaks around 60 minutes. So it seems like ERK phosphorylation activation causes an increase in EGR1 mRNA, increase in EGR1 protein, and we would suggest that that would cause an increase in EGR1 activity and increase in collagens. So what we did is just to make sure that it was ERK is we used a compound called SCH, which is an inhibitor of ERK. And if we block ERK phosphorylation, we don't see any increase in EGR1 mRNA, and we don't see any increase in EGR1 protein. So what it looks like is when we do activity, we get an increase in the activity of ERK, this kinase that's within your muscles and your tendons. When it gets activated, it binds to and increases the expression of this gene, EGR1, or the early growth response gene, and that becomes a protein that can then bind to and increase collagens. I haven't shown you that it increases collagens yet. So what we had to do is we had to actually figure out what EGR1 does, so we put it into muscle, so we can electroporate muscle. All we do is we take a gene, we can inject it into the muscle, provide a little electrical force or electrical stimulus, and that muscle now expresses our gene of interest at a quite nice high level. And when we see that as we increase EGR1 protein, or mRNA I should say, we get a linear increase in collagen expression as well. So what that says is that as we increase EGR1, we're going to get an increase in these collagens, which is going to then give us an increase in protein and increase in matrix. So now what we're trying to do is we're trying to figure out what other ways can we activate EGR1. Can we use some of the things that people are trying to develop, like electromagnetic? Can we use lasers? Can we use other things to activate EGR1 in these tissues to stimulate these tissues to grow? All right. And we've now generated EGR1 knockout mice, and I just had 4 litters born a couple of days before I came over here, so we should have data that shows whether EGR1 is required for this or not very soon. The other thing is, what type of exercise do you do to maximize EGR1? So we do a lot of engineering, we work with a lot of engineers, and engineers like using these multifactorial analyses. So interestingly, at least for EGR1 mRNA, if you do, it looks like about 13 repetitions, about 3 sets, very high load, and a very low work to rest, or a very high work to rest ratio, you get maximal EGR1 expression. So again, we're trying to figure out what types of exercise are going to increase this, and how we can then take that as something that people can use practically. All right. So what I'm going to do is I'm going to try and bring all of this molecular stuff into something that's actual practical. All right, so what we're going to do is we're going to do 2 case studies. The first is an Australian rugby player. This is a highly decorated Australian rugby player, ruptured his ACL in the tackle, and then that ACL was surgically repaired with a hamstring autograft. All right, so if we look at that individual, it's a big individual, 115 kilos, so decent calories, but that's a significant decrease from what their normal intake was. Increase the leucine content or leucine-rich protein content of the diet to try and maintain muscle mass during this period of inactivity. The important thing for us is that this individual is out of the brace 2 to 3 times a day, doing range of motion activity, loading as soon as possible. And Michael's shown beautifully that the earlier we can get load across that tissue, the better the repair is going to be, the faster it's going to be. And what we're doing is we're doing about 6 minutes of activity. Range of motion, 6 minutes of activity, and then we're going to give them 6 hours of rest in between. We give this individual 10 grams of gelatin an hour before the range of motion exercise. I'll tell you all about the nutritional components tomorrow if you're interested. That's only one of the nutritional things that we do. But basically we're giving it an hour before so that we can get the amino acids to where we want it to be. At week 4, they begin leg strength training 3 times a week with slow progression, and we're going to use heavy weight, slow movements to try and maximize the functionality of both the tendons and the ligaments that we've got. If we look at this individual, this is a different DEXA, so you have to take that into account, but fairly even with fat mass, lean mass is maintained throughout. The interesting thing for us is that hamstring strength had returned by 14 weeks already. So hamstring strength is usually very slow to recover after a hamstring autograft. We already had him back to full hamstring strength by 14 weeks. That individual was ready and able to play international rugby at 30 weeks following the ACL repair. Okay? So again, this is the type of repair that we're looking at where we're trying to use these loading parameters, very short periods with long periods of rest, a little bit of the nutrition we'll talk about tomorrow, as a way to come together to try and get something that's going to be practical and useful to get somebody back to high level. And the reason that we wanted to get him back quickly is because the World Championships were about 38 weeks. So we wanted to get him back because that was captain of the team. Second case study is going to use this idea of viscoelasticity and how you would use that to try and really target a tendinopathy. So the viscoelasticity, it means 2 things. One is that, if I load faster, I'm going to get a stiffer structure. The second thing that it means is if I load and I keep that load there, what happens is the tension in the collagen goes down over time. Think about it. I don't know if they do this in Denmark, but in Canada where I grew up, basically the gym teacher would have you sit against a wall at 90 degrees and you just sit there. It should be easy, right? You're just sitting there, your back's against the wall. It's got to be easy because you're not moving, but then your legs start to burn and everything becomes really hard. Because as you sit at that same length, the tendon is relaxing. And so your muscle has to work harder and harder to maintain your position. We take this to mean that normally what happens within a tendon is you get a good part of the tendon and a bad part of the tendon. And you get what's called stress shielding. What that means is if you take a river that's flowing really well and you put a rock in the middle of it, all the water just goes around it. The same thing happens to stress when you have a small injury in a tendon. All of the force goes around the injury, so you never get load in that injured area. So you get what's called a scar, which is non-directional collagen. Because you need the directional force in order to give you the information to know which way to synthesize your collagen. This is a male professional basketball player. You don't have to be an expert. I'm certainly not an expert in reading MRIs, but I know there's not supposed to be a white spot there. All right? This is what we call a central core tendinopathy, patellar tendinopathy. It's chronic pain for 5 years. This is quite clearly a problem. So what we're doing here when we work on this individual is this is standard whole body strength training from about August of last year. So basically this is going to be 1 year between the 2 MRIs. Athlete also played 50 professional basketball games during that time. And what we did is we integrated heavy isometric stress relaxation training. What that means is they were in a leg press machine. They would go to 90 degrees, lifting a heavy weight and just hold it there. What you're hoping is that the strong collagen from the outside of that weight hole is going to relax. And what's going to happen is that the load is also going to be felt on whatever materials and cells remain in that hole. Because what you're trying to do is you're trying to relax all the strong stuff so that you can actually get the load where it needs to be. And then 1 hour before the stress relaxation training, we gave them 15 grams of gelatin because we'd done some more research to show that a little bit more was better. This is the MRI 10 months later. You can still see a little bit of a problem there, but it's a significant improvement. Individual lost 2.5% of their body mass, significant increase in hamstring strength. We put that in as something that we wanted to be able to do. Improved range of motion. What you can see is two things. The first thing is that this white area is much smaller. Second thing is the patellar tendon is actually thicker. And if you go back to the original, there's a lot of white stuff in here. You can see it's thinner than here, where it's bigger, darker, and it's the exact same slice. So we try to control that. All right, so what we're trying to do is we're trying to get to a point where we can decrease a lot of these kind of chronic injuries by using loading, using that viscoelasticity to know that if I slowly load this with a heavy weight, what's going to happen is I'm going to get relaxation, I'm going to get sliding of the collagens near the muscle end of the tendon. I'm also going to get relaxation of the strongest collagens so that the weakest collagens get the stimulus like, oh, look, force is coming this way. We need to put our collagen going along the line of force. And so now you can increase the amount of collagen synthesis in the right direction. So the practical things that I want to leave you with is connective tissues adapt maximally to short periods of activity separated by long periods of rest. So for a lot of our athletes, what they're doing is they're doing periods where we're going to have these health-based sessions. If you have a runner who's a long-distance runner who's loading their Achilles, their patellar tendon chronically, but they're going to go out for 3 hours on their long run, that's great for their muscles and their heart. They continue to adapt over the 3 hours. The connective tissue's already stopped adapting after about 10 minutes. So what we'll do is we'll do a separate session for those tissues to try and maximize performance of those tissues. I showed you that slow movements cause shear stress near the myotendinous junction. That breaks down crosslinks and makes the tendon a little bit less stiff close to the muscle. That's why most of the physical therapists in the room know that they do slow eccentric loading for tendinopathies. And what I'm telling you is that it's not about the eccentric component, it's about the slow component. So you can do the same thing by doing slow shortening, or you can do the slowest possible contraction, which is an isometric contraction. All three of those types of contractions work to improve musculoskeletal health of the tendon. During fast movements, the collagen molecules work as a sheet. As a result, you're not getting shear forces. As a result, you're not breaking crosslinks. You're increasing crosslinks through increasing lysyl oxidase. And the result is that those tissues get stiffer if you just do fast movements. That's great for performance, but it's going to put you at an increased risk for injury. I showed you that loading increases ERK signaling, whether you're looking in the tendon, whether you're looking in the muscle. We've never known what the increase in ERK signaling was doing in muscle, but now we've shown that it increases this transcription factor EGR1, which we've shown when we just put that in, we get an increase in fibrillar collagens. And we think that that's really one of the things that's important for the increase in force as we load our muscle. Because if we just make our muscles bigger, it doesn't mean that we're necessarily making them stronger. We're just making them bigger. We can make a really big muscle that's not really strong. I know the medical doctors in the room know a number of different conditions that happens. And then I've shown you at the end that stress relaxation, using viscoelasticity to allow stress relaxation to take hold, allows us to get load across the weakest part of a tendon, even if that's the central core, which normally gets a compressive load during fast movements. If you load it slowly, now you can actually get a tensile load on it and allow the directional orientation of collagen synthesis to occur, and it really can treat a lot of the musculoskeletal issues that we've got. All right, so I'll just go back to my acknowledgments. Hevgi Amtor, who did the work with the halofunganone. Greg Shaw will talk about the work that we did together on nutrition. A lot of the work that I've had with the engineered tissues was done initially by Jennifer Paxton and then Ann Lee Bartel. And I'd be happy to take any questions from the audience.